I can find my notes there. Plane stresses in more detail. And we're going to discuss transformations and equivalent stresses for the first time. You've kind of maybe already gotten some hints from what we've talked about that when you have a couple of normal stresses, or even when you have one uniaxial normal stress, there could be some type of equivalent shear stress that matches up with that type of normal stress. Or there could be maybe a combination of normal stress and shear stress that lines up with that type of loading as well, okay? And you've also maybe got an inkling that there's a reason we like tensors, right? If you watch the video about what the heck is a tensor, okay, that's included in some of the notes. The main thing there is that tensors, or one of the main attributes of tensors, is that they preserve their information through rotation. So why am I even mentioning that? Why are we mentioning that we want to preserve the information through rotation? It's because we look at different states of rotation of an element in a state of stress to be able to then figure out, okay, is this material going to fail? Is this structure going to fail or not? Okay. Why? Because we tend to think a lot in terms of shear stresses and normal stresses. And the failure criteria we're going to discuss in a little bit are based primarily on, hey, is your loading creating shear stresses, or is it creating normal stresses, or is it creating a combination of both? And how are they going to affect whether or not your material breaks, right? The very first class, we asked, what do you want to learn in this class, in this session, or in this whatever semester, okay? Which is quite abridged. Well, it's abridged in terms of the time span, not in terms of the content, as you figured out, right? We're slowly getting there. We've talked why things break. You have an idea of why things break, but we're getting to the point where we can quantify the stresses that will lead to the failure based on a yield strength that we calculate in a tensile test. Okay? And the hope is that because we've now gone through this process of explaining, okay, this is how we characterize material properties, right? We had a lab. I hope that was helpful in terms of being able to, understand, here's the yield stress, or yield strength, here's the elastic modulus, those types of attributes. What I'm hoping, right, is that now near the end of the class, we can connect states of stress in a structure back to this is what how the material behaves, and is it going to fail or not. Okay? So today, what we're hoping to discuss is a bit on sections and equilibrium for rotated elements, and then we'll so this is a rotated element, sorry, and this is kind of just giving you a depiction of what we're going to be doing in a minute on part one. Then we'll introduce these generalized equations for 2D transformations. Okay, so essentially coming up with a way so you don't have to do part one every time, although I expect that you can do what we talk about in part one. Okay, and then you could check using information in part two, and then finally we'll talk about stress tensors and rotations. Okay, and stress tensors and rotations, right? This is a tensor, which for our intents and purposes has 6 pieces of information: sigma x, sigma y, sigma z, tau xy, tau yz, tau xz, right? And it's got a main diagonal, and then the off diagonal terms are symmetric, or have the same values. And this is how you would do a transformation. You'd actually have a rotation matrix, which I'll show you, times the stress tensor times the transform of the rotation matrix. Okay, you don't have to be able to do this on an exam. I'll show you how you can do it in Python. And it's kind of cool. So you can get the same results. You see we're introducing all these primes, x prime, y prime, sigma x prime, right? All these primes, those are what we use to describe state of stress in the rotated state. Okay. So you've seen this before. We have 6 states of stress, like we described, and we have a cube, and we start mapping our sigma x, our tau xy, our tau xz, and our tau yx, our tau yz, our sigma y, our sigma z, our tau zx, our tau zy, right? And we also understand that this is only 3 of the 6 surfaces that are shown, or 3 of the 6 surfaces are shown, right? There are 3 other ones that are on behind. Okay, and then these sigmas are associated with the traction vectors, which we also described very early on, maybe session 3 in the class. And what are the traction vectors, right? These are the vectors where if you take a slice, you're going to be able to say, we have some type of forces, internal forces acting over small dAs. So they have essentially vector format with the components of the traction vectors being the stresses. Okay. And this is a Cauchy stress tensor. And if you want to learn more about it, you can look at textbooks or Wikipedia. And we're typically not doing the sigma 1, sigma 1, 2, 1, 3, but we write them as sigma x, sigma tau xy, tau xz. And of course, if we're doing things with pre-po max in finite element analysis, then we remember these subscripts. Now, plane stress is not, it is applicable to airplanes, all right, but plane stress is referring to a 2D element, which we just talked about in the office hours in a little bit of length. And typically, we're going to say that the stress normal to the plane is 0. So the sigma z is going to be 0, whereas sigma x, sigma y could be non-zero. Sigma xy, or better said tau xy, could be non-zero as well. But the perpendicular component we say is typically 0. And the shear stress is perpendicular to the plate. So if we have an xy plane, that means the shear stress is where you have a z or a y. Where you have a z as a subscript. All right, so either tau xz or tau yz, those are going to be 0 as well. Okay, yes.
Is that supposed to say plate?
So it's plate. You can think of it a plate, or you can think of it as the plane. Okay, a plate is a thin kind of thing, right? So this is the plate, or this is a kind of an object, all right, that's kind of thinnish, and you have like these forces or these stresses or these traction vectors acting on it, and we take this element out, and we're saying, look, we're really interested in what's happening in the xy, but we don't really care what's happening in the z, or it's close to saying it's 0. And remember, I think in the video that you watched on the thin wall pressure vessels, because I didn't get to share that experience with you, which is one of my, it's just like kind of a more fun kind of thing to talk about. I'm pretty sure in that video I talked about how, we talk about hoop stress, we talk about axial stresses, right? And then we also could think a little bit about what's happening in the thickness direction of the thin walled pressure vessel. And in that thickness direction, we said that the stress is essentially 0, okay, for like a couple of reasons. One is it turns out that when you do PR over T or PR over 2T, we're talking thin stuff. So T is typically pretty small, and so the sigmas that you get are typically much higher, much higher, okay, than the internal pressure in the system, okay. And so even if you have like 1 atmosphere of pressure inside, because it's a thin walled pressure vessel, that is going to be PR over T. We're talking like it's going to be like at best 1/5. Okay, because we said that we're assuming that R is like 10 times that of the thickness at least. Okay. So anyway, in the Z direction for pressure vessels, it's we assume that pressure that is 0 in that thickness direction. And you can also think of it as you have a very sharp gradient from some P inside to essentially 0 outside the pressure vessel. Okay, and so again, it seems to be it is essentially very small. Okay, and so this is just that said all over again. Okay. Now, what do we mean when we you know, go from a 3D to a planar element? Again, I kind of said this already. You have a 3D element, and we said that pretty much we only care about sigma x, sigma y, and tau xy. Okay, and so if we draw it, okay, there's a sigma x, there's a sigma y, or sigma x, sorry, sigma y, right, and then the tau xy, and the corresponding 4 arrows. Okay, and so 2D representation is just roll over it with a car and look at it as a flat plate or plane. Okay, and so you look at the top-down perspective, and this is the standard way of drawing a 2D element. Okay, standard way. Even if I have like a YZ, like if I replace X with Y and I replace Y with Z, okay, I would still end up with arrows going into this corner and arrows going to the bottom left corner. Okay, that's just this is the conventional way of drawing it, and it's also following the convention we said, right? That this is the X face and this is the positive Y direction, and that's tau xy. So this is the one I look at the box and I say, oh, okay, start on the right side, because that's going to give me my positive horizontal face. And sigma x and sigma y are pretty self-explanatory. All right, but this is how we draw a 2D state of stress on a planar element. Now, if we begin to think about transformations, what are we talking about? Okay, we are defining a state of stress at a point. Okay, and that point, might have been in some type of object. So you've got we've got all kinds of structures at this point, right? We got maybe something like here's the state of stress at this location. We've tried to line up our elements with the axes of our problem, right? Like we've said, okay, if this is x, right, and this is y, and x cross y, this is z, right? I'm going to map a little element that's got an x face, a y face, and a z face. Right? That makes life easy. In reality, though, those are useful constructs for us, but that's not necessarily what the physical world cares about. Right? Like the tree falling down doesn't say, hey, I want to fall down perfectly about the x-axis for you. Right? That doesn't care, right? Those are things that we define. So now you can kind of begin to think, maybe we should be able to think about the state of stress in a more convenient set of coordinate axes, but then rotated by some amount. All right, and of course, you can rotate about x-axis, about y-axis, and about z-axis. And if when you do dynamics, I don't know if you do definitely in graduate dynamics, we talk about these Euler angles and things of that nature, and these rotations and fixed angle versus, or body fixed versus coordinate fixed rotations and things of that nature. But here, we're just trying to keep it simple in that let's rotate. You know, we said we didn't care about what's happening in the z direction, or we said, you know, sigma z is going to be 0, and the tau yz and the tau xz are going to be 0, and you know, but we can, let's rotate about that z-axis, and let's define that rotation as being something that we can describe with a theta. Okay. Now, you can kind of believe, maybe more than just because I say it, that I would like both of these descriptions to be equivalent to each other. And I would like them to both have the same information. And you're like, there's that word tensor coming up again, right? I want them to be the same. So I can go to this state and I can rotate. And then if I rotate again, right, there's going to be a whole set of angles, right? Infinite number of angles, essentially, that I can rotate by. And I essentially have I want to be able to get back to that original state of stress. Or, you know, I could in some way rotate to get back to that original state of stress. And all of these states of stress that I have are going to be equivalent, and they're all going to satisfy equilibrium. That is the key, right? Because we're doing statics. Well, that's not why, I guess. Because these elements are not accelerating, right? And so one thing that has to be clear, right? I cannot draw sigma x on one surface and not draw on the other surface. Because if I did that, and because you know sigma x times whatever the small dA might be, right? It would lead to a force which would lead to acceleration. Or a tau xy times a dA times a radius, or you know, a delta x over 2, whatever it would be, would lead to an angular acceleration if it was not balanced appropriately. So one thing that remains true, okay, with all this mess is that we need transformations of stress which maintain equilibrium. Okay? So that's our path. That's our path, okay, to being able to go from one state of stress to another state of stress that's been for an element that's rotated. They both have to satisfy equilibrium. So like, oh, well, I know all about that. I know how to satisfy equilibrium. I satisfy equilibrium by summing moments and summing or summing forces, right, and setting them equal to 0. And in this case, what we really do primarily, we don't really care too much about the moments. We care a lot, though, about the stresses and we care a lot about the forces summing to 0. Okay, so we have to come up with forces, though. So here is a little bit kind of process of how you do this. So you start with the element having known stresses. Okay, and I guess I'm kind of maybe foreshadowing a little bit here. You're again doing equilibrium to balance forces. Yes, you end up coming up with equivalent stresses, but we're not balancing stresses. We're balancing forces, right? Just like you can't add sigma x and sigma y to each other, right? They're orthogonal to each other, right? I can't go from a sigma x prime to sigma x just with adding them together. Now, you know, there's a lot of tricks. I mean, that's a little bit unclear, right? But to do equilibrium, I need forces. And so how do we get forces? Well, we're going to need to figure out what the effective areas are on which these stresses are acting to be able to do balance. Okay, so this, we still haven't drawn an area. Okay, so don't fret. I'm foreshadowing a little bit, but this is just to show that, again, I'm going from one state of stress to another state of stress by an angle theta. So we rotate by angle theta, and now question is, how do we relate these new stresses to the old stresses? And this is where it gets wacky. All right, we're gonna take some cuts, we're gonna expose some faces, okay, and we're going to do it with a face perpendicular to x prime. Like, what? A face perpendicular to x prime. Okay, so first off, we have been dealing with coordinate system x and coordinate system xy, or xyz really, okay? With coordinate axes xy primarily, and z coming on the page. So what is the x prime axis and what is the y prime axis? Okay, so what this is supposed to show, okay, this is a triangle, duh, all right? This face of the triangle, right, is supposed to be, take a cut with exposed face with perpendicular, that's not English. Okay. Come on, you can do it. No, you can't do it. Okay. Still can't do it. Oh no. Oh no. Oh no, what did I just do? No, not good. Come on, PowerPoint. Okay, well, I want to say that if I wait a minute, equilibrium will return. Oh, that's not fun. I might have just crashed. Like nothing's responding. Oh, okay, that's good. All right, let's try. Let's see. Well, before I crash it. Okay, great. Okay, so this is, okay, take cut with exposed face perpendicular to x prime. Okay, or take cut with exposed face with perpendicular. I guess maybe it's English in some way, but I think it sounds better this other way. Okay, so this now is a face x prime, like that. Okay. And this is that face, right? That's purple, all right? And then these green ones are, corresponding to, this face is corresponding to x, and then this face down here is corresponding to y. And there's an angle theta between x and x prime. Here's the new y prime, like this, okay, that direction. And this is now a delta A. Okay, that's the face that we care about its area. Or we care about the area of that face, the one that's perpendicular to x prime. Can you see this? You gotta be able to draw these. Okay, you gotta be able to draw these. Right. Now, let's go and take a look at this. When we draw these, highly recommend that you exaggerate. That you never make one of these triangles 45, 45, 90. Because you won't know which angle is the theta. Alright? You'll know what theta is and what you know what 90 minus theta is. Alright, but if you do 45 or 45, 90, you won't know which one's which. And that makes things tricky for the transformations. So look, this theta is less than 45 degrees. Okay? This angle in here is less than 45 degrees. this we'll say is supposed to be larger than 45 degrees. All right. Again, I maybe didn't exaggerate as much. When I say exaggerate, I mean like make these things look like that. Okay, so that you know that this is the theta like this, and this is the theta in here, like that. Okay, and so then it becomes obvious that this face, and since if this face is delta A, this is going to be delta A sine theta. Okay. What delta A, I mean, this is kind of weird. I'm just drawing a 2D figure, right? You know, like that's annoying. Yeah, it's annoying. And what we're saying is that there's some depth into the board, essentially. Right? Really, this is a triangle, right? Where I have side, right? You know, this is the hypotenuse. This is the, well, it depends. From here, you know, this is going to be opposite, and this one's going to be the adjacent. But, you know, this is really like some kind of like wackio prism, okay, that's like in the board, right? But anyway, I digress. So that's where the delta A comes. The delta is because these are supposed to be infinitesimally small elements, right? These are material elements, so that's why we call it delta A. Everyone see this? If you got this down, we're halfway there, okay? Now, this one's delta A cosine, and this is where it starts to get real interesting. Now, you see, I did a little bit better job exaggerating things here, just a little bit. Think about acting, or these stresses now acting on these areas. This is the delta A face, like this, right? So now I can think of a force associated with this face, its area, and stress sigma x prime. I can think of a force associated with tau x prime y prime, you know, times the delta A. So now we're getting to forces. And we also can draw forces that were associated with the original sigma x, the original sigma y, all right, and the original tau xy. All right, so you've got your OGs over here, and you've got your, I don't know what is the opposite of an OG? Huh? Modern. Okay, your current, your upstarts. Okay, your x prime, y prime. Right. This is like Wemby over here, and this is like MJ over here, right? Something like that. All right. So we can map these. We can relate these to each other through equilibrium. All right. And you see, this is kind of wacky because now we say sigma y times the delta A sine theta, right? That's a force, okay? Tau xy times the delta A cosine theta, that's a force, all right? And we have all these forces. And we can do equilibrium. We know the angles, right? And we know the we know the areas, we know the directions, we know the magnitudes of the stresses. So we can do equilibrium. Okay? This is on the x prime cut. And you'll see that sometimes if you want all the information, okay, we have to do a y prime cut. So what does a y prime cut look like? Well, y prime cut is going to be looking at a face that has y prime coming out of it, like this. Remember, y prime was just going along this one, right? So this, you know, typically what happens is I can figure out what sigma x prime is and tau x prime y prime are from an x prime face cut, like this, right? But notice there is no sigma y prime here, right? When I say no, I mean the bottom one. There's no sigma y prime. So in order to get sigma y prime, we've got to do a y prime face cut, like this. Now sigma y prime comes out, and now there are another set of equations for equilibrium. Either one of these cuts, either on the x prime face or the y prime face, will be sufficient to figure out what the new tau x prime y prime is. Okay? These are not indeterminate systems, right? That's very nice. You get two equations, right, to solve for two unknowns. Delta A just knocks itself out, right? Delta A is not really an unknown. It's just a dummy variable that helps us, okay, to balance forces. But the two unknowns that we have here, at least if you're going from a state of stress of sigma x, sigma y, tau xy, to this new rotation with a theta, you're going to figure out on the bottom one, you're going to figure out what sigma x prime is and what tau x prime y prime would be. Those are the two unknowns. And then in this one on the right, the two unknowns would be tau x prime y prime and sigma y prime. Okay. So typically, unless it's asking for sigma y prime, I use the one on the bottom. Okay, that cut. Yes. Yes, Tavia.
Why did you do the y cut and turn it horizontal when it's originally vertical? Is it because you want to take a cut like perpendicular?
Yeah, because I need a cut that's perpendicular to the y.
Okay.
All right, or that allows y prime, sigma y prime. I need y prime to come out of that face. Perpendicularly, yes. Right? And you can kind of see, so where is it? This face right here maps to this face up here. Okay, so let's look at this. This is, so now the drawing is half the battle here. I don't know how you do this if you don't draw it, okay? And so you've got to be able to draw it. Here's example 17.1. If the state of stress on an element has sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equal to 0. What are sigma x prime, sigma y prime, and tau x prime when the angle of counterclockwise rotation is 30 degrees? Okay. So, there are a couple things. One, we know since it's asking for both sigma x prime and sigma y prime, we're going to have to do two cuts, all right? If it had just asked for sigma x prime and tau x y prime, if it just asked for sigma x prime and tau x prime y prime, then we only have to do a cut perpendicular to the x prime, or a face perpendicular to the x prime coordinate axis, okay? But since it's asking for both, or since I'm asking for both, it's an opportunity for us to see how to do this equilibrium on both faces. Okay, so this is the state of stress that we have originally. The state of stress that we're going for, okay, is with a rotation of theta equals 30 degrees. In reality, you don't worry about drawing it, exactly 30 degrees. Just put a theta in there, okay? And we're going to rotate this sigma x prime by that theta, okay? And we're going to go ahead and designate the corresponding new stresses that we want, like this. Okay. So once again, please exaggerate the angles. Okay. And here we go. Here's our attempt at trying to make things work out. We have our x prime face, or axes, okay? And then, in reality, what I would do, I wouldn't draw these x prime. I would draw the triangle first, okay? Sorry, I should have probably done it. It's not animating in that order. But draw the triangle first, then draw x prime coming out of this face, okay? And again, this is not going to give us sigma y prime. This is going to give us the relationships for tau x prime, y prime, and sigma x prime. Okay. Now we have our delta A over here. We have our delta A sine theta there, and we have our delta A cosine theta over there. We have our sigma x, which is the 50 megapascals coming out over there. We have this interestingly new vector, sigma x prime, okay, which is aligned with x prime. We had our sigma y coming down straight down, and now we draw another one that is in a line with the y prime. You see this? Because we have these exaggerated angles, I don't have to think too much, right, about where I draw the theta. Because the theta is the one that's less than 45 degrees. Okay? So I draw the theta in the tiny angle, and I leave the other one unnamed. All right, and I need one over here, and I need one over here, right? But I could, oh shoot, is theta this one or is theta this one, right? This is why you draw it exaggerated. Okay, now we got to do some equilibrium. Or we're almost ready to do equilibrium, okay? So the summation of the forces in the x prime direction are going to be equal to 0. X prime, so what are they talking about? What am I talking about? Well, now we think about x prime, and we think about y prime, and we're saying x prime. Okay, fine. Well, what are my knowns? My knowns are this 100 here and this 50 megapascal here. So this 50 megapascal or this sigma x up here and this sigma y down here. Okay. My unknown is sigma x prime. All right, but sigma x prime is of course in line with x prime. Okay. So there are going to be a few things that pop out here. What is sigma x prime doing? Well, if I'm in the x prime direction, sigma x prime is already in that direction. And what's the force associated with sigma x prime? Well, it's just sigma x prime times delta A. Right? I'm assuming that I have this uniform stress acting along the entirety of each of these surfaces. Okay? So that sigma x prime times this delta A will give me the contribution of force, right, that's going in the x prime direction. So that I write. Now I have a choice. I'm going to either look at the y contribution or the x contribution to the problem and transpose it appropriately to be in the x prime direction. So, first off, what area is 50 megapascals acting on? Well, it's acting on this face, and this face looks big, at least it looks big compared to this one, but it's not as big as this hypotenuse. You know, that hypotenuse face. I don't even know what the adjective form, what's the adjective form of hypotenuse? I don't know. The hypotenuse face. Noun modifying noun. Not appropriate always. But anyway, here we go. Noun modifying noun, hypotenuse face is this one. Delta A cosine theta is the face that the sigma x is acting on. All right, but I only want the component that's perpendicular, I only want the component that's in line with x prime, right? So you see that 50 megapascals is acting on this left face, and that face has area of delta A cosine 30 of degrees, but it's not, the 50 sigma x obviously is not aligned with sigma x prime. But if I look at this as another triangle, and I say 50 is the hypotenuse of that triangle, then the adjacent side of that triangle is aligned with x prime. And I can use that vector on this area with this equilibrium in the x prime direction. Okay? So you tell me, what expression do I write next for the 50 megapascal, for the sigma x? Yes. Okay, 50 delta A cosine 30 degrees, yes, times. Okay,
Times another cosine 30.
times another cosine of 30 degrees, yes. That's right, because that gives me now this side of this vector of that triangle. Okay, so 50 cosine 30, and it's, you know, times delta A cosine 30. Does everyone see this? All right. You'll be happy to know that there are shortcuts to this. But what we're trying to do today is show how we're in fact satisfying equilibrium when we do these rotations. Okay. Now, there's another contribution in the x prime direction, and that is from the 100 megapascals. That is from the sigma y. Right. Oh, and I guess we should have said, yes, this is going opposite direction of x prime, so there's a minus sign. Okay. This is when vector addition is very important to remember. And always is a harsh term for me. I get confused quite a bit with vector addition. Actually, I get more confused with vector subtraction. That's when I get confused with it, right? So what I think about, right, is that this vector plus that vector is going to be equal to the phi hypotenuse. Okay. So when I draw this triangle out, I have to think this vector plus this vector in that direction is going to be equal to this hypotenuse. Okay. So which one of these is this in line with x prime? No. Is this one aligned with x prime? Yes. Is it contributing in the positive x prime direction or the minus x prime direction? And that is why you have to do vector addition first. That you know, yes, I draw the arrow down to the left on that for that particular 100 megapascal hypotenuse. Okay. So now what is the next expression? Someone want to take a shot? Yes, Andrew.
So L minus 100 sine 30 times delta A something.
Yes. Okay, and that's it. Okay, there are no other faces, right, with vectors with stresses that are contributing to this equilibrium in this x prime direction. Yes.
I'm still kind of confused how
Yeah.
delta A cosine 30 is included as well.
Yeah.
Like, is it also going in that direction, the same direction as 50, or?
So the delta A, so yes, that face is parallel to the y direction and is perpendicular to the x direction. And it serves as the area on which sigma y is acting. Right? Sigma y is acting perpendicular to this this y face, right? That's a normal stress. That's what a normal stress does, right? It acts normal to it. So I got to figure out what the force is. The force in the minus y direction is 100 megapascals times delta A sine 30 degrees. Okay? Because that's the length of that face. But then that has a component that is aligned with the y prime face. Okay? Or sorry, it has a component that's aligned with the x prime face. Okay, the x prime direction, right? So not x prime face. The y prime face or the x prime direction. Okay, so that is that's what we use when we do the equilibrium. Okay. Da 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 da. So now we can solve for sigma x prime. So that's what sigma x prime is. If we want to know our tau x prime y prime, then we need to look at equilibrium in the y prime direction. And you see that tau x prime y prime is acting on this face in the y prime direction. And that y prime, that face on which tau x prime y prime is acting is going to have area delta A. So that's what it is. Tau x prime y prime times delta A, and that's it. But now I have to go back to these contributions from sigma x and sigma y, right, and look at the appropriate sides of these right triangles to be able to do equilibrium. So I have this vector right here, okay, which is still contributing it's in the y prime direction. It's positive there. So I have this 50 megapascals times the delta A cosine 30 times sine of 30 degrees in order to give me this force vector. Okay, that's acting in the y prime direction. And I've got, okay, so we do that all out. Okay. A little bit more. All right. Okay, you see that everyone sees that, right? And then we do the same thing coming down to sigma y. And which one is acting in the y prime? Well, it's this adjacent side of that triangle, at least with theta put right here, that's in the same, or it's actually in the opposite direction as y prime. So there's going to be a minus sign, and it's acting on the delta A sine 30 degree face, and this is going to be in the cosine 30 degree direction. Okay. And this is what you get there. And that's going to all be equal to 0, and then we can solve for tau x prime y prime. Okay. So we've done our first transformation problem. Woohoo! All right, we've done our first rotation. Now we have a new couple components of stress for this new rotation. But we've still missing sigma y prime. Yes.
You know what delta A is?
Okay, delta A is something we define arbitrarily. Okay, and we're going to say that delta A in this case is essentially the x prime face of whatever element that we draw is. So for that new rotated element, delta A, or that delta A is the area associated with the x prime face.
How did you solve for the stresses?
Okay, how do you need the algebra from here to here? Well, look, delta A all knocks out. There's a delta A, delta A, delta A. So they all go, you just divide everything by delta A. Right? And then everything is known except for sigma x prime. Okay, is that good? All right, good question, Joshua. I glossed over that. Yes.
What part exactly on that triangle is delta A, and what part exactly is delta A sine 30 and delta A cosine?
Yeah. So delta A is from here to here, right? So from the top to this bottom right, okay? Delta A cosine 30 is from the top to the bottom left, and delta A sine 30 is from this bottom left to the bottom right.
And is A just a letter we chose, or does it represent area?
It represents area.
Okay.
Right, but like I said before, right, this is assuming it has some depth.
Oh.
But the
okay.
depth is all the same. I mean, I could have called it like, I don't know.
So because the depth doesn't really play a role in this problem, we don't even care about it.
Well, we care about it because we need forces. And so to have a force with a stress, you need an area.
We just need to know that it exists, though, right?
We just need to think that it's the same for every single one of these sides of the triangle.
Okay.
Yes. And do that.
How do you know what direction you draw that, like the bottom arrow from the purple?
The purple one?
Yeah,
Okay.
the orange one?
So which one? Which direction? Okay. So I need first, I need the direction, one of the directions to be in line with my original x and y, right? So this one has to be, since it's coming out of the bottom face, like a y face, or minus y face, it has to be aligned with the y direction, okay? And similarly, this one for sigma x has to be aligned with the x direction, okay? And then the other face needs to be aligned with x prime, right? Of that, the other side of that triangle. So, and the other side of this triangle needs to be aligned with the y prime, okay? And then this one needs to be aligned with x prime, and this one needs to be aligned with y prime, okay? Remember, if I have a vector and I know its magnitude, which you do, sigma x and sigma y, we know the magnitude of these vectors. Those are the hypotenuses. And then I split it into two directions, or that make a right triangle. And those are going to have smaller values, right? But those, the x, right, an x prime contribution, a y prime contribution, that then sums up to the original x, right? X and y, those are the hypotenuses that I'm interested in. Just like, well, it's not even a very, no, I won't even say that, okay? X prime and y prime, those are things that we want to know, so we pick a delta A that is already perpendicular to them, so we don't have to do more acrobatic transformations. Does that help answer the question?
Okay, wait, so the bottom, like the small ones, they go in the, or the orange one, it goes in the y prime, and then the purple one, it goes in the x prime, but why is it drawn to the left and not the right?
Because of vector addition.
Okay.
Right? Because I need, let's say I start them both here at this point. I need two vectors to get me from here to here. Right? I could do all kinds of vectors, right? There are all kinds of vectors that could potentially, I could do like this, right? And I could do this, right? Those vectors, if I add them together, will give me this same magnitude. Okay? But I don't want to do that because these vectors are not in line with my x prime and my y prime. Right? They're not helpful. They're only helpful because they're only helpful if they line up with my new coordinate system. So I have to pick two sides of those right triangles that line up with the new coordinate system. Okay? And I need them to add those two sides I picked, I need them to add. That's why I said don't do vector and subtract. I get confused with vector subtraction because I could think 50 megapascals minus that one side is going to equal to positive on that side, right? No, I just go from that starting point, I go junk and junk, and I make sure I draw the arrows appropriately so that they add up to that hypotenuse. Okay. Good questions. We're running out of time. This is example 17-1. Shoot, guys. We got work to do. Okay, but this is important. Once you get this, then the rest comes out so nicely. Oh, no. We're not. That clock is all messed up. Okay, we have a lot more time. Let's finish this example, then I want to sit for like 30 seconds. I've been standing for a long time. All right, so you guys might want to stand. I want to sit for 30 seconds because anyway, we started office hours way early. Okay, so this is the same kind of thing. We're looking at now trying to figure out what sigma y prime is. Okay, for this rotation. So we cut this triangle so that we have a delta A that is going to be essentially the y prime face. Okay, delta A is the y prime face. And now we have delta A sine 30 degrees, which is going to be associated with the x face. And we have a delta A cosine 30 degrees, which is associated with, well, a minus y face. Okay, so again, we draw these triangles, okay, that correspond to adding up to the sigma x and the sigma y. All right, and I think, Divya, you had a good question there. It's like, why do you draw in the way you do? And it's because we need this to this plus this to add up to that. Okay, and we need this plus this to add up to that. And we choose smartly so that, you know, this one's aligned with x prime and this side is aligned with y prime. And this is aligned with y prime and this is aligned with x prime. No, I'm sorry. This is aligned with x prime. This is aligned with y prime, and this is the original x direction. Okay. All right, and now, yeah, we have the tau x prime y prime there, right? And again, we do similar thing. We're going to do equilibrium in two directions, but instead of x prime, sorry, no. Well, instead of last time we did x prime first, it doesn't really matter, but we got to do it in x prime and y prime. But instead of having an equation for sigma x prime, we don't have any representation of sigma x prime in this drawing, right? But we have representations. Unknowns are sigma y prime and tau x prime y prime. The tau x prime y prime has got to be exactly the same as what we got last time, okay? So if you've already done the other problem, like we did on the previous slide, then don't, like you see, okay, tau x prime y prime, that's in the x prime direction, Don't do the summation of the forces in the x prime direction because that's going to waste your time. What we really need to do is figure out what sigma y prime is because we already know tau x prime y prime. Anyway, like we sound really super nerdy. Tau x prime, y prime, sigma x. I mean, it's like, who cares about, anyway. So, sigma y prime times delta A, that's this area on which it's acting. And let's do sigma x first. So what is the sigma x contribution to our y prime equilibrium? Yeah, how do you? Oh, you're thinking. Okay, I thought it was
Did you say the sigma x contribution?
yeah, let's say sigma x contribution.
Where is sigma x?
Well, which one is it? I mean, this goes back to the previous slide, I guess, right? Sigma x was, yeah, go ahead.
Oh, wait.
Did it? Yes.
Is it
Yeah, it's a 50. 50 megapascals is the x, sigma x. And the sigma y is 100 megapascals. Okay, go for it. Come on.
So is it 50 times sine 30 times delta A sine 30?
Yeah. All right, you got it. Okay. Okay, and then do you want to take us through the sigma y contribution? Yeah, I agree with you on the minus part.
Minus 100 times
Remember, we're doing y prime, right? And this is why we do exaggerated. Which one of these is theta? This one or this one? The tiny one's theta, right? So if we're interested in this, yeah.
100 times cosine
Yep.
30
Mm-hmm.
times delta A cosine 30.
That's right. Okay. And that equals 0. And then you can solve using Python, if you like, right, for sigma y prime. This is accounting, right? It's like you gotta keep track of things, right? But it's not that hard. There's just so many of those spots where you can make a careless mistake. That's unfortunate, right? Any questions? We good? All right, let's I'm gonna take just a 20-second breather here. Whew. All right, now,
My notebook's at 4%.
huh?
My notebook's about to die. It's at
Your notebook's at 4%,
Yeah.
and yours is like one of those fancy never die things.
Oh, I haven't charged it in a week and a half.
Oh, so 4% for you is like what, another 2 hours, right?
Maybe. We'll find out.
You've like never gotten that down to.
I started at 10% and I've been using this since
office hours.
Oh yeah, okay. Well, that is impressive. Yeah, I looked into some of those e-ink things, and I've almost bought one multiple times, but I've not decided.
It's worth it for me.
It is? Okay, that's good. Can you look at PDFs on it?
Yes, I can connect to the Google Drive. The only thing I will say is because it's eating, scrolling is a little chunky.
Okay, all right. Because like if you could draw on PDFs, that would be really cool.
I think you can, it's just I haven't worked it out yet.
Yeah. Okay. Yeah. And it's like, I just wanted to do this. No, I wanted to do this. I wanted to do this one. Oh, I'm right back to a Windows tablet. You know. So anyway, all right. So this problem is something you might see where they say, oh, you're going to take a slice at an arbitrary angle, okay, just like this angle that you see right here, okay, and we're going to say sigma x prime is normal and to the right of the shown slice. All right. So what in the world is this talking about? Well, right of the slice, I mean, I guess this is where you gotta follow the words pretty carefully, right? And if it's sigma x is normal to it, so that means that sigma x is going to be coming out of this plane in this direction, okay? And so, you know, the way we defined theta before, this would be like a negative theta. It'd be like going below the horizontal. So here's what the element looks like. And we've gone down 30 degrees, and we're coming out of the sigma x prime like that. Okay? And then the element also has a sigma y prime coming out the top, and it has a tau x prime, tau y prime, or tau x prime y prime as shown as well. Okay? And equilibrium is maybe a little bit different, but it's you know, this is maybe where it's, I don't know, just better to use drawings, better than to try to overthink things too much. So this is a small angle, and if we draw something exaggerated, okay, and let's draw something that exposes an x prime face. So maybe let's draw a triangle where this y prime direction is the hypotenuse. Okay, so what does that look like? It looks kind of like this. Okay, you see this face right here is this face of the element. This is going to be our x prime face, right? And this is going to be the y prime direction. So again, I've drawn it exaggerated so you can see that this little angle in here is 30 degrees. This is 60 degrees, right? Maybe that's not that exaggerated. It probably could be more exaggerated. Probably be easier to read if it was exaggerated, but at some point I lose space. But you will have lots of pieces of paper on your next exam, like you had on the first exam, right? You didn't need nearly all that. No one, I had so much. Oh, I have your exams, by the way. Sorry, before I forget. The paper ones. You already have the digital versions, but I have the paper ones I'll give you at the end. So anyway, this is a sigma x prime coming out. This is a delta A on this face, so this is going to be delta A sine 30 degrees. This is going to be delta A cosine on this face. All right. Then it gets a little bit tricky here because here's the sigma x coming out this face, and then and that's the hypotenuse, and then I have two vectors that I use to complete a right triangle with one side of that vector, one side of that triangle in line with the sigma x, or in line with the x prime x prime direction, and the other in line with the y prime direction. But we only need to figure out well, actually, they say what are sigma. Okay, so we need to know sigma x prime and tau x prime y prime. So for that, we're going to have to do equilibrium in two directions. Okay, so we'll just draw it all out though. okay, so that, yeah, that's the sigma y split up. Okay, and what's fun here now, okay, what does the green represent? We didn't have the green one before. And it's maybe not fun, but what does that represent? The green triangle. Yes?
That's additional shear stress that's being added.
Yes. That's a tau xy. Remember in the first example, there was no tau xy. Now we have tau xy. As if it weren't complicated enough. All right. So that's the tau xy, and it has the hypotenuse, of course, is the tau xy, and we have the two components that are going to be helping us do equilibrium in the x prime. This is x prime direction, and this is in the y prime direction. Okay, and what do you know? Tau xy doesn't just act on one face; it acts on two faces. Okay. And again, we're going to break that hypotenuse into two components that we can add up to each other, and one's aligned with the x prime, this one's aligned with x prime, and this one's aligned with y prime. Yes?
All of the triangles that we're drawing were supposed to be right triangles, right? Or are they just supposed to be vector summations?
Supposed to be right triangles because, yes, x prime and y prime are in fact orthogonal to each other. Yes?
Is which arrow corresponds with 75 on both?
Ah, yeah, the horizontal top one. And the vertical, on the left, the vertical one, yes. Those, because that 75 is, in fact, is aligned, right, with the, well, that's the tau x prime, y prime, right? And that is, and on one face it's in the x direction, on the other face it's in the y direction. Okay. Let's see, is this thing, is it going to see me? Yeah, okay, maybe. All right, so we can now draw our tau x prime y prime if we want, and we can do equilibrium in the x direction and equilibrium in the in the x prime direction and equilibrium in the y prime direction. I need to go a little bit faster, but you get the idea here at this point, okay, that we're going to do these summations, and now we also have contributions from the taus. And so before you saw that there were like only two of these crazy terms. When you have sigma x, sigma y, and tau xy, you get 4 terms that you had to keep track of, plus, or with the, the term you're trying to solve for which you're trying to solve. Okay, and if you want, you can do some Python code, and this is what sigma x prime is. Okay. But we do need to get going because there's a lot to cover. All right, and then similarly, we can do in the in the y prime direction, and we can solve for tau x prime y prime. And in this case, again, we have these 4 terms that we are going to use in conjunction with the tau x prime y prime times delta a, and we do equilibrium, and we get the following. Okay. All right. So in the homework, you're going to have a question, okay, that's going to look at a state of stress associated with a pressure vessel, a thin-walled pressure vessel. And this thin-walled pressure vessel would have a longitudinal, right, and a hoop stress. The hoop stress is the larger of the two, and it's twice what the axial stress is, okay? And so in this case, just be careful. This is the hoop direction. Do you see that? Even though it's horizontal, it's not the longitudinal direction because of the way I drew the vectors. The vectors are larger here than they are in this vertical direction. So hoop is, around the circumference. Okay. And then rotate 45 degrees, and let's see what you get, all right, for the shear stress. And then there will be another question, right, where you have another slice like this, okay, and you can attack that one, okay, and that is just the first part of this. Okay, it'll get better. Generalized equations for 2D transformed elements. Guess what? You can come up with general equations. I don't have to plug in numbers every single time, right? You saw we did like 150 megapascals, we did 50 megapascals. I can just leave it in terms of sigma x, leave it in terms of sigma y, and do some algebra, okay? And so that's what we're coming up with. We come up with a general set of equations for these transformations, okay? Now, it's still important to, I always have to think, this always gets me confused. Okay, what is a slice? What is a slice? Because that's what we were talking about, slices, right? Look, if this is the slice and this is the smallish angle here, all right, that corresponds to a rotation, okay, about z like this. And you see that this slice, this was sigma x coming out this face, now sigma x is coming out kind of like this, right? You see that? And you see that then if I kept extending that, that angle right there is the theta. Okay. So this is how we can begin to map slices to rotations. So you slice an element is the same thing as rotating the element, but you just got to know which one is which face of the slice. Yes, positive x, positive y, yeah, and theta, right? And theta, of course, is typically positive when it's following the right-hand rule. Here you go. These are the general equations that we just solve for manually. And then you do some algebra, trigonometry, and voila. You get a sigma x prime equals this big mess. Similarly, you do this, 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 and voila. You get a tau x prime, y prime is equal to this. And you can do the same thing for sigma y prime. Or you can think of sigma y prime as equal to sigma x prime with theta plus 90 degrees. Okay, because it's 90 degrees from it. Okay. And so these are the equations. You want to write these down. Yeah, we definitely want to have those down on our formula sheet. Not because I'll necessarily ask you to compute them, but because I might ask you to do the other method and you want to check afterward, okay? Or you're going to learn a new method that we'll talk about in, very soon, in fact. All right, very soon, that will allow you to bypass these equations. At least, I hope it allows you to bypass them. Some people will never bypass these equations, all right? But there is a way to think about transformations that is super nice and super graphical and super not having to do all these equations, okay? And we'll show you how to do that in a little bit. So in this example, this is just saying, hey, if I have a rotation of 30 degrees, plug them into the equations, what is the new sigma x prime, right? So theta goes in here, here, right? Sigma x, sigma y go in here and here, and tau xy go here. Tau xy was equal to 0, so this part goes away. And so now instead of doing all that free body diagram business, right, you've got kind of simple calculations. Yes?
Are the formulas on the previous page, are they good for any shape and cut, or was it just for that specific cut?
They're good for any rotation, right? So if you have a slice and I say, this is the slice, you still got to figure out, okay, which angle am I really plugging in? Which is the equivalent angle that I use for rotation? Okay. So it's not like, how do you say it? These equations are for rotation, right? And we know slices map to rotations, but you gotta be careful with any of these slices.
Right.
Okay. So this is super fast if you have a calculator, right? Or maybe you program this into your programmable calculator. Whatever you want to do, right? But this is how you figure out these transformations very quickly. And let's just say that you wanted to see the state of stress on an element as you rotate from 0 to 180 degrees. Well, this would be sigma x prime. This would be the tau x prime y prime. And this would be the sigma y prime. Like that. Okay, that's just plotting, right? All I did is go from 0 to 180 degrees, and that's what you see. And you can kind of see that this thing is periodic, right? And once you go 180 degrees, right, you're back where you started, right? Every one of these, you're back where you started. And that makes sense, right? Because you've now flipped, you had your sigma x over here, and now whoop, your sigma x is on the other side, coming out the other direction. So it all maps out nice. Any questions on this? Okay, so you have another question. All right. This, I suggest what you do is you use the collab. There is collab, right? And you can just look at the collab numbers and you say, please submit the value closest to 0 degrees. As theta plus or minus degrees is also a solution, all right? So it's like, hey, what is the angle of rotation you have to have in order to get tau x y prime to be equal to 0, right? So you can look at the tau x prime y prime equation, and then you can just look at the graph and say, oh, that's the amount of angle I have to do. And then finally, for this session, we have the opportunity to think about stress tensors and rotations. This will be quick, and you don't need to know this for the exam. But if you are doing rotation about an axis, there are rotation matrices associated with them. And which rotation matrix is of interest? Not usually Rx in our case, not usually Ry, but the Z, right? Because we're rotating everything about Z. Okay, so this orange one is, the biggie, all right? And this is the one that you can apply in the tensorial rotation. So if you want to rotate, so this is maybe if you were going to, plug things into your calculator and you can do matrices, and you say, hey, I want to rotate by theta equals 15 degrees. This is the fast way to do it. You have an RZ over here, then you have the transpose of RZ over here, and then you have your original tensor right here, and the new sigma prime will give you the new state of stress. Okay, and there's Colab that does this for you, all right, and you can get some experience running that Colab if you like. And then there's this kind of question, all right. This question, I'll let you think about it a little bit when you get to it, and if you have questions, ask me in the chat, okay? But this one is, you don't actually have to do, you can use the rotation matrix stuff if you want, okay, to rotate 90 degrees about the positive x-axis. So this is not that, how do you say it? It's not the z one, it's the x one. But you can think about it. You don't even have to do any of that. You can just kind of think, oh, if I rotate 90 degrees, okay, what are now my new x prime, y prime, z prime? And what are the original vectors of stress doing in those new coordinate systems? Right? So it doesn't even really require any math. It's just more like an optical, a mental rotational exercise. And that's it. Okay? Let's go on to the next one for 27 minutes. So what are we responsible for for Monday on the exam? Up to you. Okay. You have nothing due on Monday, right? These questions are due on Tuesday, but you do want to be able to do. You want to be able to do the slicing. Okay, you want to be able to do the slicing by Monday. So that's the only new thing you have to learn. Only new thing you have to learn. Okay, before Monday. So make sure you can do the slicing. Okay, but now we're going to go on. I'm going to stop this, and then we're going to go on to the next session.